Good morning. This is the first episode where we'll be really going over a actual paper here, and the paper that I chose to begin with and I attached to this YouTube video is a paper from 2023 called Data-Centric Artificial Intelligence. And it's a survey paper, so it's very nice because it covers everything really up to that point that pertained to the use of data in neural networks, what had worked up to then. This is a particularly valuable resource because today, for example, we know much less about how data is actually used in the frontier AI companies. Most US companies now do not publish at all on their essentially techniques. Those are considered trade secrets. So they might publish a paper with some collaborative group on like alignment work or safety work, or even publish some benchmarks that other companies can use to evaluate their models. But publications on the techniques that are actually being used under the hood to improve model performance, those are no longer really reported by American companies. So this is kind of an interesting snapshot in history, and I think it's very likely that the techniques that are identified here are still being used in those frontier companies, but with some differences which I'll try to point out as we go along here. So this paper really covers how data is used to train models. So first of all, why is data so important? So there are essentially three different techniques that one can use to train models. There's supervised learning, unsupervised learning, and reinforcement learning. So supervised learning requires labeled data. So you need, for example, the classic example is you get an image of a cat, and then you have a label that says this is a cat. So you can run the image through your neural network, and you get an output. And then if the output says cat, and it is a cat, the label also says cat, like it matches the label, then you reinforce. You say thumbs up to that particular response. If not, if it gets the wrong, if it says not cat when the label actually is a cat, then the weights of the model are adjusted appropriately so that it's more likely to output cat in the future for that input. So that's supervised learning. Unsupervised learning, you still need data, but it doesn't need to be labeled. And generally that's a lot better because labeling data, at least it used to be, very intensive and very annoying, and comes with all sorts of problems. So unsupervised learning, you just give the model a bunch of data, and it's really the model finds patterns in the data. It applies some like clustering techniques, and so it finds groupings for the data and classifications, and it helps it to perform some tasks in the future. So this is a lot better. And then best of all, from a data standpoint, is reinforcement learning. Because reinforcement learning, you simply let the model go in an environment and act in an environment according to a certain policy. And usually with reinforcement learning, you want an environment that really has you want an environment where you can easily verify the model's actions in the environment, that they're positive or negative. And then if you can do that, then you can reward the model if it does a good action, and change it appropriately when it does a bad action, and so you can improve the model's performance without really any data. It's just a model acting in an environment and learning as it goes. So now, probably this is still true today, and it definitely was true back in 2023, where really the heart of the most impressive neural networks, the heart was supervised learning. This was, in a sense, like the simplest technique, the easiest technique, but it was also the technique that was most effective. So you just give the model a bunch of labeled data, and it learns things from that. So, for example, for the GPT model, for the GPT models, it's a next word prediction, next token prediction for the model. So you feed some input prompt and it gives you a prediction for what the next token is. And of course the internet is full of text data. So you could essentially use the entire internet as labeled data, and you get around the labeling problem, because you can give go to some random Reddit page and feed in the first sentence and then predict what the next token is. The model can try to predict it, and there is a right answer because this Reddit post does have a next token. And you can use that over all the data on the internet, and you get a pretty good model here that you can get on the other side of that really kind of seems to understand human speech and text and how it's formatted. So supervised learning is so essential. And on top of that, there's also the scaling laws, which is were laws that were arrived to that shows what parameters you can fiddle with to improve model performance. And one of the most important parameters is data size. So it turns out if you just train on more data, the model gets better. If you hold the data fixed and you just increase model size, you will actually get diminishing returns of improvement. So if you're scaling up the model, you want to scale up the data alongside the model size to get best possible performance. So what that triggered was a race to collect as much data as possible. So text data on the internet was one, but there's people went literally anywhere to try to get good data to feed in. And so there was essentially an issue that began to arise. And the issue was that, first of all, we were running out of data. And second of all, that the data that you're getting was of lower and lower quality. So if you have low quality data, so if you have low quality data or perhaps skewed data, then your model's performance will actually go down. Will get worse because that low quality data is affecting the outputs of the model. So, and skewed data where if you have, for example, certain things let's say there's very little actual coding in the database of the model that it's being trained on, but there's a lot on medicine, for example. There's a ton of stuff on medicine, but very few things on coding. The model's not going to be very good at coding in that case. So you kind of have to have a representative data that will teach the model broadly all the things that you want it to be able to do. So now all sorts of techniques were developed to essentially deal with this. So for the first problem, the running out of data, the techniques to deal with this are something called, for example, data augmentation. So data augmentation is where you essentially can scale up, can multiply the amount of data that you have available by doing some small modifications to the data that you have. So, for example, the classic example of this for text data was for teaching a model translation. So if you wanted to be good at translation, what you do is you take the initial text that you have, you feed it into the model and have it translate it to a foreign language, say French. So it translates this text into French, and then you take the French text that it just translated and you feed it back into the model to translate it to English, and then you compare that output to your initial input in English as well. And so you can compare them, and if the closer that it is, the more you reward your model. So that's a way that, for example, I can use all my English data to train my model to translate from English to French and French to English by using this data augmentation technique. And there are all these other clever tricks. So for example, another classic example is for images and image classification or something like this. So you have an image and you have something in the image and you want the model to be able to tell what that is in the image. So it can say airplane or car or something. So what you do is you take an image and you have the model output what it thinks that image is, and you have that's labeled data. you crop the image to make it slightly smaller, and then you feed that image in, and you keep the same label for the image. So this is a technique that you can massively upscale the amount of data that you have without increasing much human labor in adding labeling. So that's a technique, data augmentation. There's more intense technique that is synthetic data, where you're actually producing data, usually to try to get out of distribution data. So like, this is a concept where you have in distribution versus out of distribution. In distribution is generally the data in the training set, and so if the data in the training set doesn't really generalize very well to the outside world, then your model will do very poorly when it's actually deployed, because once it's deployed, it got used to, it got really, really good. It's like overfitted to the training data, and so it goes out into the wild, and now it's not as good in the outside world. So you can do synthetic data generation with GANs, usually, to try to develop new data, especially in the areas where the model is weakest, and try to feed that into the data set to improve it. But all of this is synthetic data, data augmentation. And the third thing is data maintenance. So this was a very important thing, especially towards the beginning of the ramp up in models, which is how do you filter out harmful data? So data maintenance is this concept that you want your data that you use for training to be representative of the stuff that you want your model to do, to be robust enough so that the model can generalize to stuff out of distribution as well. And you want it to be high quality enough that you can make sure that you're kind of getting the best bang for your buck with the data that you're using. So what you effectively do is you can slice the data into different things. So for example, you can say this is the data that is because of coding, or even subdivide within coding. So you can have data associated with coding in Python, data associated with coding in C++, and so forth and so on. And then you can fiddle with how you are using the data so that you get a good balance that gives you the performance that you're looking for. So this is the concept of data maintenance, of trying to get something that is that has a distribution that you want, that gives you the performance that you want, and filtering out bad data. So this is all the concept of data maintenance. There's a lot that can continue to be said about this, but I'll just pause here and discuss very briefly the best way to avoid these problems altogether. So the best way is to not rely on data. So this is a lot of what's driving the progress now is techniques like reinforcement learning, especially in fields where you can easily verify the answer. So you can do this, for example, coding is an excellent example like this, and it's why so many companies are so focused on coding and improving model performance in coding. Not only is it because coding, like if a model is good at coding, it can pretty much do almost anything in the modern world, but not only because of that, and also it can improve itself, which is rather scary and dangerous. But it's not just that. It's that for reinforcement learning, you do not need to have you don't need to do this alchemy with like data and getting exactly the right data and trying to look for it and making sure that it's clean and good. You can sort of just let the model go, and you're not restricted by the amount of human data you have, and the model can just improve by itself at scales that wouldn't be possible if you were bound to human generated data. So this is what's driving a lot of the current push, and why probably models will continue to improve in domains where improve most rapidly in domains where the answer can be easily verified. In places where answers are not easily verified, that's a place where you can kind of use RLHF, reinforcement learning with human feedback, which is a whole other discussion that we can go into. But very briefly, it's use humans to judge model outputs, and they don't need to judge everything. They just need to judge a small amount of model outputs, relatively small, and the model will essentially learn from these small examples what the kind of thing that humans are looking for. And so it can sort of label things as good or bad itself without having to rely on humans labeling literally everything for it. So that's like related. RLHF is sort of also related to another technique that's kind of similar but also different, called semi-supervised learning. And in this technique, it's sort of like a mixture of supervised and unsupervised. You give some labeling for some of the data that you receive. The model takes these labels and modifies them, improves them as it goes through a much larger amount of unsupervised learning of a much larger amount of data, and learns from that, and it's more efficient than just if you did unsupervised all the way through. At producing like model understanding of features that is more in alignment with the understanding that humans have, with categories that humans have, and so can make the models more useful. So that's pretty much it. Thank you very much for listening, and I feel like I didn't actually go into a lot of these concepts are sort of like talked about in this paper, and but perhaps in a future episode I can go in more detail about what they actually did in this paper and the resources that they were discussing. So I hope that this was enjoyable and informative, and I'll talk to you guys later.